Okay, so first thing we're going to do is we're going to finish up section 6.1. So we've talked a little bit about degrees and radians, how to convert between the two. We're going to look at a formula today that you have to use radians in the formula. So if they start you off in the word problem with a degree, we got to fix that right away to use the formula I'm going to show you. So the formula we're going to talk about first is called arc length. Basically, it's a way to figure out how much, or the measure of part of a circumference of a circle. Now, what we're going to do is we're going to derive the formula, which means we're going to figure out where it comes from. But we're going to start with this fact. The fact that arc size and angle size are directly proportional. And I'm going to draw that out and show you a picture of what that means. But arc size and angle size are directly proportional. So here's a circle. Here is an angle. How much is that angle? 90. Here's the arc that a 90-degree angle makes. Okay. How much of the circle does that take up? It's a quarter. Right, let's draw another circle. Now what I'm going to do is I want to double the size of that angle in green. If I double it, it's going to go from 90 to how much? 180. So here's my initial, here's my terminal, here's my arc. I doubled the size of the angle. What happened to the size of the arc? It doubled. That's what directly proportional means. If you double the size of the angle, you double the size of the arc. If you made the angle half as big, you would make the arc half as big. Changing one directly changes the other exactly the same way. That's directly proportional. So, because these two things are directly proportional, we can set up a proportion. We can set up a proportion to be able to figure out what's the formula for arc length. So, we're going to start with this diagram and try to figure out how to set up a proportion from this. S represents the length of an arc in red. Theta represents an angle. So what I've drawn is I've drawn two angles and two arcs. R, what do you think that stands for? That's your radius. Yep. So arc size and angle size are directly proportional. So let's see if we can set up a proportion. Now, there's lots of ways you can set up this proportion. You've got 4 spots. You've got 4 things you have to plug in. As long as, however, you set it up on the left, you do the same on the right, you're good. So, anyone, and there's a lot of ways you can do it, have a thought what I could put in this left fraction using 2 out of 4 of those circled things. This is to this as that is to that. Yeah?
Theta over S.
Sure. Theta over S. So he compared angle to arc. So we have to set the right-hand side up the same way. Angle to arc. Any questions on that proportion? This angle is to this arc as this angle is to this arc. That's a directly proportional relationship, which we already drew out and said, yeah, it is directly proportional. If it wasn't, you couldn't set up a proportion. Okay. Now, unfortunately, a proportion with 4 variables in it doesn't do much for you. It's kind of like if I wanted to convert, and I keep going back to something simple, like feet to inches. You can't have feet, inches, and have it blank. You've got to have something filled in. So, if we had a fact, we could put right there that we already know is true. That's all we need. So, in this case, what's a fact here I could fill in that's true? 1 foot is what? 12 inches. Now, you've filled in a piece of information to start with. You could tell me either one of these. You could say, well, I want to know 8.5 feet is how many inches? Fine, just cross multiply and I can figure it out. But the key is I had to start with something I already knew was true. Okay, like previous knowledge. That's exactly what we have to do here. We have to start with something we already know is true. And there is something I told you yesterday. So, let's suppose that theta 1 is 1 radian. Okay? And if you're like, well, how can you just suppose that it's 1 radian? Well, how can you just suppose 12 inches? You don't have to pick 12. I heard somebody else say something. You could have done this. That would work too. You got to suppose something, right? Something that you know the answer to. Okay? 3 feet, I know the answer is 36. 1 foot, I know the answer is 12. 1 radian, I know the answer because of something we learned yesterday. Killing some trees, Mr. Bab. Suppose theta 1 is 1 radian. Does anybody remember how the size of the arc and the radius are connected if you have an angle that's 1 radian? They're the same, right? So if you suppose that your angle is 1 radian, it automatically tells you the length of your arc. You automatically know it because the connection between arc and radius is exactly the same if the angle is 1 radian. So this fact right here that I just circled, that's going to be like our 1 foot 12 inches. If the angle is 1 radian, then your arc is r. That's the fact we're going to use to start with. So we're going to fill in those 2 pieces of information on the right-hand side of our proportion. Let's fill it in and see what we get. So theta over s equals 1 over r. Again, how did we know that? That's like prior knowledge. That's the 1 foot 12 inches. It's just a fact we already know to be true from something else we learned. Now, how do you simplify a proportion? What do you do? Cross multiply. I'm just going to erase this because I'm going to put some more circles in here. What's s times 1?
S.
And then r times theta? Just r times theta. That is what we call the arc length formula. S equals r theta. Now to use it, there's 3 variables. You have to be given 2 of them. As long as you know 2 out of 3, you can solve for the 3rd. Right? And this whole equation is based off of a directly proportional relationship. Okay. So S is your arc length, R is your radius, and now theta, you got to be careful. Scroll back up. When we started this off, we supposed that our angle was in a radian unit. That means this formula is based off things being in radians. So anything that you plug into this formula, it's got to be in radians. If I give you S and R, and you solve for theta, the answer that you get is in radians. Okay? This formula is all about radians. Okay. Any question on the arc length formula? Right. Let's try an example. I think we left off with example 5 yesterday. If you want to start example 1, you can, but I just continued. So this is a problem where they write everything out and they give you a picture. It says, find the length of the arc, that's what's in red, of a circle with a radius of 2, and the angle of the size of the angle inside the circle is pi over 4. What unit is this pi over 4 in? How do you know?
Because it doesn't have a degree sign.
It doesn't have a degree sign. You can't say, well, because it has pi. Nope, radians don't always have pi, but it does not have a degree sign. So what's my, Derek, what's my formula for arc length?
S equals radius times angle.
S equals, radius times angle. Okay, so read what it's asking. Find the arc length. So we don't know that. Radius, 2. You can either look in the picture or just read it. Radius is 2. I'm not worried about putting inches on it. I'm going to worry about the unit at the end of the problem. What's my angle? Pi over 4. Yep.
When you do this formula, does it always have to be in radians, or can you do it in degrees and it still be fine?
No, it's got to be radians. Yep, it has to be radians. So basically just multiply it out. What's 2 times pi over 4? Yeah, 2 pi over 4, or if you reduce it, pi over 2. Now we need a label on that. What did I just find?
Inches.
What?
You found the arc length.
I found the
unit
arc
should
length.
be inches.
The unit should be inches. If you're finding, there's 2 options in this formula. You either have an angular measurement or a length measurement. That's length. Length in this problem is inches. It's pi over 2 inches. If they wanted it as a decimal, you could plug that in, use the pi button, divide by 2, and you'll get about 1.57 inches. They didn't say to do a decimal here, so I'm not going to bother.
So in the unit circle, the radius is always 1, right?
Correct.
So in the unit circle, if we have an angle in radians, is that the same length as the arc always? Because you're just multiplying it by 1?
Yes.
Okay.
Arc and angle are exactly the same in a unit circle. Yep. Okay, so that's an example where they gave you r, they gave you theta. Theta was already in radians to start. Let's look at this one. Little different. Okay, a couple things different. First of all, the directions are to find the radius. They're telling you the arc length up front is 3 pi feet. And they're saying the angle is 60 degrees. So what they're asking for is different. The way they've given you the angle is different. They didn't give you a picture. I don't think you really need a picture. You just need the formula. Okay. Skylar, what's my formula?
S equals radius and angle.
Yep. S equals radius times angle. Now, before I even use that formula, what should I take care of first? Yep.
Make the degree radius.
We're going to make the degree into radians. So I just kind of do that off to the side. Does anybody remember if you multiply by pi, divide by 180? What do you get?
Pi over 3.
That's pi over 3. Okay, so that's what we want to use in our formula. Was I given S? Arc length is 3 pi. Let's go to the next letter. Was I given R? No, because the directions I find are. Was I given theta? Yes. And what do I fill in? Not 60. Pi over 3. Okay. So now we want to get R by itself. It's kind of like getting R by itself in something like this. Basically the same idea. How could I move the pi and the 3 to the other side at the same time? Divide by pi over 3, so that's what you, like here, you could divide by 2/3, which is the same as what? Multiply by the reciprocal. Times 3 over pi, times 3 over pi. 3's are gone, pi's are gone, pi's are gone. And what do I get for a radius? 9. And now we ask ourselves, okay, is a radius an angular measurement or linear? It's linear. It's a length. 9 feet. Okay, any questions on that one? So that time you had to solve for R. The first time you had to solve for S. Anyone think they need to see one where you're solving for theta? Basically, to solve for theta, you would end up doing S divided by R. And you would get theta. Now remember, that formula will always give you the answer in radians. It could say at the end of the problem, solve for theta, write your answer in degrees. So if you use this formula, you got one more step when you're done, and that's to convert it to degrees. If the directions asked for that. Okay. Any questions on that? Okay, so that's the arc length formula. That's all that we're going to do with that. Last thing in section 6.1 is what's called angular velocity. Has anybody heard of that before or used it? Probably be a physics thing. Okay. So basically, angular velocity is used to measure the speed of something on a circular path. Okay. So it's used to measure the speed of basically something that spins. Okay. So I have, at home I have a Dremel. I don't know if you know what that is, but it's like a little power tool. You put attachments in it, and it's a variable speed. Okay? The slowest it goes is 5,000 RPMs. That means if I put a tool in it, that tool is going to spin around 5,000 times. So it's like a drill, but it's a lot faster. It spins 5,000 times per minute. The fastest it goes is 30,000 RPMs. So that means the bit is spinning around 30,000 times in 1 second, or minute. RPM is revolutions per minute. We could figure out how many revolutions per second it is if we know how many per minute. That's the kind of stuff we're going to do. Right? But it's the speed of something spinning. Engine speed on a car. Okay? Your speed of your tire is measured in like miles per hour. The speed of your engine, how fast something is spinning, it's RPMs again. Usually it goes like from like 0 up to like maybe 9,000 RPMs. It's usually what you see. Okay, so RPMs is things spinning in a circular path. All right, so let's look at this, and I just kind of want to take this disk and do something with it and explain why we even need to have angular speed. Okay, we already have linear speed. What's wrong with miles per hour? Why don't we just use that for everything? Or kilometers per hour? Anybody know why we need to have this different kind of speed? Like, why don't they just describe the speed of my Dremel to me as like 200 miles an hour or something? Why do they say 5,000 RPMs?
Because it doesn't travel in miles or anything like that.
Okay, because it's not really traveling in miles. It would be like if I put it on the ground and it didn't lose traction, maybe it would take off on me. Like a sander might do that. A Dremel's not going to do that. But yeah, it's not really traveling. It's staying still. But yeah.
It's not moving away from central location.
So yeah, it's orbiting like a central point. Now, you can still try to describe something orbiting a central point in miles per hour. You can. But watch what happens if we do that. So I've got 3 dots here. The black dot, which is kind of at the center. The next one out from the center is red. And then the outermost dot is black again. Now, I'm going to take this circle. And what I'm going to do is just do 1 revolution. Just like that. All right. So I just did 1 revolution. Now, out of these 3 dots, which one traveled the farthest?
The outermost.
The outermost one. That one traveled the farthest. Now, if you look at the inner dot, that one really didn't move at all. If it was right at the center, it wouldn't look like it moved. And the red dot kind of traveled the middle amount. Okay, so they all had an orbit kind of about that center. All right. So the outer one traveled the farthest. Now, compare the amount of time it takes for all 3 of these dots for me to go like this. Going around. How much time did it take the middle one versus the red one versus the black one to do each of their movements? The same. That's a problem. So now you're saying they all did something in the same amount of time, but this one went further. So what does that mean? If something goes further than something else in the same amount of time, it's going faster. So technically, when you spin this disk 1 time, this dot is traveling faster than the red dot, which is traveling even faster than the dot in the center, because it's going farther in the same amount of time. So think about that. If you're driving and you go further than someone else in an hour, well, you must have been going faster than them. Or they found a wormhole. I don't know. But other than that, all these dots are going different speeds. So that gets confusing to describe the speed of this disk. It depends where on the disk you are, if you're going to use linear speed. Now, if we use angular speed, and I describe this revolution, I can say all those dots completed a revolution, and maybe it took me 2 seconds to drag it around. This dot did a revolution in 2 seconds, so did the red one, so did the outer black one. They all did 1 revolution in 2 seconds. If we describe it that way, they all have the same rotational speed. That's why we use angular speed. Any question on that? I'm not saying they're traveling the same distance, they're not. But they're all traveling at the same angular speed. Okay? So, in our book, angular speed, kind of the default is always radians per time unit. Okay, time unit's not important. Could be radians per second, radians per minute, radians per hour, but it's radians per something. So, I mention this because if you do when you do the homework, it's going to say find the angular speed, and it's not going to tell you the units to use. This is the units I'm telling you to use, radians. There's other angular measurements. The 2 big ones are degrees and rotations. I see rotations a lot, and I see it all the time in real life, RPMs. So most real life things that I know about use our revolutions. We're going to use radians. Okay. So you compare that to linear speed. Linear speed is like if cops on the side of the road, they point a radar gun at you and then they get your speed. Right? That's how fast your car was going on the road. Not how fast. The cop doesn't pull you over because your engine was doing 4,000 RPMs. Okay. The cop pulls you over for linear speed. So that can be measured in a linear unit, feet, inches, centimeters, kilometers, whatever, per time unit. Hours is a common unit, but you can have seconds too. I think miles per hour is the easiest one for people to associate with. Like if I tell you something is traveling, 200 feet per second. Can you imagine? Is that how fast I go on the highway? Is that 200 feet every second? It's hard to kind of think about it. But miles per hour, we kind of associate with that. Just like most people in here probably aren't that familiar with kilometers per hour. So if I said like 100 kilometers an hour, I mean, is that really fast? Is that kind of fast? What is that? So you can come up with formulas to try to convert, like all kinds of special formulas to convert different things. But the easiest way to do it is kind of how we've been converting degrees and radians. If you want to cancel out a unit, just make sure it's in the other spot in the fraction. That's how we'll do this. Okay, so that's called dimensional. We're analyzing our dimensions. Feet, inches, whatever they are. You do need to know a lot of common conversions. Okay. So things that I would expect you to know, seconds, how many seconds in a minute, minutes in an hour, hours in a day, days in a year. How many inches in a foot, feet in a yard, how many feet in a mile, days in a year, things like that. Okay. You're not going to have to know an obscure conversion like how many centimeters in a foot. That's weird. It's kind of a weird number. But you have to know like the basic ones. Okay, so let's start out with something that's not even a rate. Okay, a rate is like distance per time. This is just time. Just want to convert 3 days to minutes. Now, I don't know any fancy conversion to jump from days to seconds. What I do know is days to hours, and then I know hours to minutes, and then I know minutes to seconds. So we'll do it step by step. So what's the next unit down from a day getting towards our unit of minutes?
Hours.
Hours. What's the connection between days and hours? 24 and a 1. So it's either going to be a 24 and a 1 or a 1 and a 24. Where do you want days to go? Bottom. Days is going to go on the bottom. Hours is going to go on the top. 24 of those in one of those. Technically 1 day, 1 day is. Okay, so now days in the top, days in the bottom. If you did that out, you'd be left with hours. Okay. What's the next unit down from hours? Minutes. What's the connection between hours to minutes? 60 to 1. So, where do you want hours? Bottom? 60 minutes, 1 hour. Hours in the top, hours in the bottom. Now, if you do it, you'd be left with minutes, which is what you want. Okay. If they wanted seconds, I'd have to go one more step. If it's confusing because the first number wasn't a fraction, just think of it as over 1. Multiply straight across. Denominator doesn't matter in this problem. It's just 1 times 1 times 1. So we've got 3 times 24 times 60. Well, what's 3 times 60? So it's 180 times 24. 80 times 24. So it's 4,320 minutes. Okay. So simple problem, just converting a time unit to a different time unit. Now, let's look at a rate. Okay. 50 feet per second. So now we're dealing with 2 units. Feet, seconds. They want both of them changed. Feet to miles, seconds to hours. Do each one at a time. So what does this really mean? 50 feet per second. What does that mean? 50 feet per 1 second. So you're going 50 feet
50 seconds per second.
in 1 second. Now, we can choose at this point, do we want to deal with the length unit or the time unit? Which one do we want to do first? Length. Okay. So we need a connection between feet and miles. You don't really have to go feet to yards and then yards to miles because it's a somewhat common number for how many feet in a mile. So, what's that number?
5280.
Yep, 5,280.
Makes me want to pop in my mouth. That number.
5,280 feet in 1 mile. Feet's gone. Now you've got a speed in miles per second. All right. Now we want to get seconds up to hours. You might know how many seconds are in an hour, but if you do, you could go right from seconds to hours. If you don't, we can go from seconds to minutes. So Pat, how do you want to do it? Seconds to minutes or jump right to hours?
To minutes.
Minutes, okay. What's the connection between seconds and minutes?
60 to 1
60 to 1, and where do you want seconds?
on top.
Top. 60 seconds. 1 minute. Now you've got a speed in miles per minute. Vinny, what's my last fraction to get minutes to hours?
There's 60 minutes.
60 minutes. 1 hour. Minutes. Minutes. Now you've got miles per hour. So this is going to be one I think we should be able to visualize how fast this is. So what does it mean if you're traveling 50 feet every second? How fast is that really? Let's see. So it's 50 times 1, and then 60 times 60 is how much?
1,600.
Okay, so the top is 1.8 million divided by, it's all ones except the 5280. 5280. So that's,
You add an extra 0.
yeah, I got an extra zero.
Divide by 10.
Let me fix it. So 50 times 50 times 3,600. There we go. Divided by 5280. Yeah, that was way too fast. 34.1 miles per hour. So if you're traveling 34 miles an hour, and you basically look down for 1 second, you'll have already gone 50 feet. So this classroom is probably about maybe 25, maybe 30 feet. So it's more than the length of this classroom in 1 second. So now if you bump it up to highway, you're going like 60 miles an hour. That's probably Well, if we said 70, just to double it, 68. If you're going 68, that's 100 feet every second. So if you think about a football field, you'd basically travel the length of a football field in a little over 3 seconds. So you look down for 2, you've already gone 2/3 of the way down a football field if you were going 68 miles an hour. Okay, so that was a linear speed to a linear speed. Now we're going to try an angular speed to an angular speed. 200 radians per second, and I want to get it into revolutions per minute. So first thing you do, start with your fraction, 200 over 1. 200 radians, 1 second. Okay, let's get the time unit out of the way because that one's easy. 60 seconds in a minute. Now I have to get radians to revolutions. This is a conversion you would have to know. How many radians in a revolution?
2 pi.
2 pi. If you didn't know that, you could start with, well, I know how many degrees are in a revolution, 360, and then change 360 to radians by hand. That's a lot longer way to do it. But 2 pi radians in 1 revolution. Where do we want radians? Bottom. 2 pi radians, 1 rev. Radians is gone. We can even just divide this 2 into there, just to make it a little simpler. You could divide the 2 into anything in the top, but I divided 2 into 200. So I'm left with 100 times 60, which is how much? 6,000 divided by pi. So it's a little under 2,000. What's that going to be? 6,000 divided by pi. It's by 1900 maybe? 1909. So we'll go 1909.9. That was the unit, revolutions per minute. Now, revolutions per minute is kind of a common one, so you can do this. Or you can write RPM. That's what RPM. RPM does not stand for anything other than revolutions per minute. So if you ask somebody, what's RPM? If you look it up, that's what it'll say. Same thing with miles per hour. That's a common one. So if you put MPH, that's okay. All right, last one for this.
Per man. What happens if you're trying to find
So this one says that a wheel with a radius of 18 inches is rotating at 1,850 RPMs. Okay, so a radius of 18 inches, that's a lot bigger than a car tire. That's like a car tire that would be 3 feet across. So it's probably more like a tractor. Yeah. Big. So a wheel with a radius of 18 inches is rotating at that speed. I'm not going to do part A, because part A is to convert RPMs to radians per second. We basically just did that. We converted revolutions per minute and radians per second. We just kind of did something like that. I think we did it, let's see, they want converting to radians per second. Here we converted from radians per second. So it would be the same idea. So let's do part B. So part B says find the linear speed of a point on the circumference of the wheel. The way you can kind of visualize this is if this tire was spinning on like a balancing machine, and all of a sudden it came off the machine and it hit the ground, and it didn't lose any traction, which isn't realistic, but if it hit the ground, and the second it hit the ground, all of its rotational energy went into moving it forward, how fast would it be going? If you were standing in front of it and had a radar gun, how fast is it coming at you? Same idea. If you had like a rock on the end of a rope and you were swinging it, and your rope was 18 inches long, and you were swinging it 1,850 RPMs, very fast. and you let it go, all of a sudden the rock would take off in a straight line. How fast is it going? Okay, same idea. So that's what you're finding. So let's start with that speed. Anytime you want to convert from an angular speed to a linear speed, revolutions is kind of the bridge to do it. You don't want to be in radians per second. You don't want to be degrees per second. You want to be in revolutions. 1,850 revs. What was it per minute? All right, let's get it to seconds first. That's the easy one. How do I get minutes to seconds? Multiply by 60. 60 minutes, 1 second. Now, I have to get revolution to feet. That's not a standard conversion. Right?
It's the other way around. Yeah, I was looking at that and I was like, wait a minute. Am I crazy?
Yeah, who said multiply by 60? Why do I listen to you?
I really have to.
I was
You know,
like,
like, good question.
no, as soon as you wrote it, I was like,
Okay, now we're good. So converting, the next step is to get rid of revolutions. Even if you don't know the conversion yet, where is revolutions going to go? It's going to go in the bottom. Feet is going to go in the top. That's a special conversion. Okay. Seconds to minutes, minutes to hours, feet to yards. Those conversions are the same, no matter what problem you ever do. Feet to revolution? No. You have to find that conversion in your specific problem. Okay? Depends on how big of a revolution you're making, which controls how many feet would be in it. So, we've got to figure out how many feet. Basically, imagine here's your tire with a radius of 18 inches. Imagine it's rolling on the ground. It starts right there. Imagine it rolls one time and it stops right there. What we basically have to do is figure this out. That part that I just put that wavy line on is really the what of the wheel? It's the circumference. So if we can figure out how big the circumference is, that will tell us how many feet in one revolution. Another way to imagine it is imagine this is like a piece of wire and you cut it and you laid it out flat. That's how long one revolution is. So we need the formula for circumference. What's the formula for circumference?
2r pi or
Yeah.
just the thing pi.
2 pi r, same thing, 2r pi. What's my radius in this case?
18.
Now it's 18 inches, but I'm going to do something at the same time because I'm trying to get feet. So I could do a separate conversion, but I tried to pick a number that was easy. How many, 18 inches is how many feet?
1.5.
It's 1.5. Okay? So 1.5, which means my circumference is how many feet? 3 pi. So, one revolution of this tire, if you were to roll it along the ground, would be exactly that long. Okay? The circumference formula is what you use to go from revolutions to feet, or inches, or whatever. So, 3 pi feet in one revolution. Okay, now let's see what we get. We can reduce that a little bit. 3 goes into itself once. And I could, I guess if I wanted, I could divide top and bottom by 10. So 2 and 185. I still need a calculator though. So 185 times 1 times 1
32.5.
divided by,
no, it's times pi.
yeah, I gotta do times pi.
Oh, yeah.
And then divide by 20. I can't really do it in my head. So 185 pi, 185 pi, divided by 1, 2, and 1. So just divide by 2. Okay, so that's 290.6 feet per second. So just put that here. So if you compare that to the speed we found before,
This is a literal
I think we had like 34 feet per second. I mean, this is way faster speed.
That tractor.
Yes,
What if you like didn't reduce it? Like what if you?
it'd be fine. Yeah, if you did 1,850,
You still
well,
get 290.
you should still get 290 as long as I didn't make a mistake. Yeah. Yeah.
So once you find the circumference, it's always over 1 revolution.
Yes, the circumference is a revolution.
Okay.
The circumference is a
So
revolution.
you have to find the circumference first.
You always have to find circumference, yep. When you're converting between angular and linear. Okay, any question on that? Yes? Is this going to be on the test? Yes. All right, so the last section for this week, which, like I said, we're not gonna finish today at all, is 6-2. So we'll do a little bit of it today, and then we'll finish whatever we can
So this
tomorrow.
isn't on the homework today?
This part is, yeah. So there's 2 parts to 6.2. The second part of 6.2 is not on the homework tonight. I'm not even gonna get to it.
So for the test, are we just gonna have to watch the video before to know?
I think tomorrow we'll get through most of 6.2. We have an hour. I think we'll be okay, because I'm not going to be able to go over a lot of homework tomorrow. So that's going to save 20 minutes.
Right.
All right, so let me just kind of explain first what unit circle trig is. Okay, the idea of unit circle trig, it's all about finding a coordinate. That's basically what it is. It's figuring out a coordinate. You draw an angle that has an initial side and a terminal side. If you do that, the terminal side is going to come out from the center and it's going to hit the edge of that circle somewhere. Our goal is to figure out the coordinate for where that terminal side hits the edge of the
I
circle.
could do that so easy.
That's the whole goal. Any question on the goal? Now, that's easy to do for certain angles. In fact, when we do unit circle trig, we can only easily find the coordinate if this angle right here is an multiple of 30 or 45. If I gave you an angle that was like 53.7 degrees, we can't do unit circle trig with that. It's going to be way too hard to figure out this coordinate. Okay? So we're only going to figure it out if it's a multiple of 30 or 45. But that's the goal. And I think that's what I just said to you. So for certain angles, by certain angles I mean multiples of 30 and 45, you can draw them in a circle and sketch the arc, and the arc has an endpoint right here. That's where the arc would end. That endpoint has a coordinate, which we can figure out. Well, if you know unit circle trig. If you can't figure out that coordinate, then you can't do unit circle trig at all. Unit circle trig is all based on knowing 2 numbers, an x number and a y number. You have to be able to get those 2 values. And if you can figure those out, then we can figure out what are called the 6 trig functions. Okay, so this is going to be the first time we've seen them in this class. I'm talking about like sine, cosine, tangent, secant, cosecant, cotangent. Those are all functions in trigonometry that basically describe something about the angle. Sine, cosine, and tangent are the 3 most common, but we'll look at all 6. Not as much detail on the other 3. Sine, cosine, and tangent we do a lot. Okay, so any questions on what I just said about finding the coordinate? Okay. So I'm going to give you the definitions of all 6 trig functions based on knowing an xy coordinate. If I ask you for the sine of an angle, first you'd have to draw that angle. Here's your circle. You'd have to get your angle, something like that. Find that coordinate, and then once you find it, I'm interested in the y value. If I ask you about sine. If I ask you a problem about cosine, you draw your angle, put a dot where the terminal side hits the circle, get the coordinate, and all I want to know is the x value. So for sine and cosine, you actually don't even need the whole coordinate. For sine, you just need the y. For cosine, you need the x. For tangent, you need both. If I ask you what is the tangent of the angle, I want you to take the y and divide by the x. And again, if you're wondering what does tangent even mean, it's kind of like asking, well, what does square root mean? It's something that you can do to a number, and it changes it somehow, and you get a different answer. Right? Same thing with like logarithm. Let's see. What's a logarithm? Well, it's a function. You can take a number, you can plug it in, and you'll get a different number out. Okay, logarithm does something to the number. All of these functions do something to the number. I'm showing you how to calculate what they do. Sine gives you the y value. Cosine gives you the x. Tangent gives you the y over x. Now, below them I put all the abbreviations. Every trig function has a 3-letter abbreviation. Most of the time it's just the first 3 letters. But not with cosecant. How come? We already use COS. So what they do for cosecant is they use the syllables. Cosecant. Now, I put them in a chart like this on purpose. 3 on the left, 3 on the right, because they are all reciprocals. The ones that are across from each other. Y is not a fraction, but you could think of it as a fraction if you want. You could always put it over 1. So if cosecant is the reciprocal, what do you think the formula is for cosecant? 1 over y. That's why if you know the 3 on the left, you automatically know the 3 on the right. You just take the one on the left and flip it. Secant is 1 over x. And how about cotangent? X over y. Yep. Yeah, so all we have left is just practicing examples using these definitions. But that's the last thing you're going to need for like content. So now we just have some examples. Any question on that? So those are your formulas. So just to kind of did I mention that? Okay. Quadrantal angles, that's just a special name that they call 0, 90, 180, and 270. I'm not sure if I ever mentioned that. I don't know. But those are called quadrantal angles because they are angles that are right on the axes. And the axes divide things into quadrants. So if you see that term in the book, it means it's one of those 4 numbers. Must be a reason why I'm mentioning that. I think it comes up in the homework. They use that term. Okay, so to summarize how we do unit circle trig. Okay, I've said it a couple times. I just want to make sure people get it. Find the coordinate. Okay. Find the coordinate. Have the x, you got to have the y. Now, sometimes the coordinate will be given to you. In the first example, I'm going to give you the coordinate.
Yeah.
There's the x, there's the y right there. There's nothing for you to find. Okay? Sometimes you're going to have to find the coordinate. I'll show you the ones that I give you today. It's going to be super easy to find the coordinate. I'll show you how. You probably already know how to do it. So, find the coordinate if you need to, and then step 2 is plug in the coordinate into the formula. Which formula? Whichever one they want you to do. If they want you to do sine, use the y. Cosine, use the x. We'll practice all 6, because on the test you don't know which one of the 6 I'll give you. Maybe I'll give you a problem that has sine in it. I'll give you another one that has tangent.
Do we have to memorize them?
Yes. you have to know sine is y, cosine is x, tangent is y over x. Yep. Okay, so find the point, plug it in. Let's try an example. So, it says the point below represents an angle. Find the 6 trig functions. I don't care, Al. I don't care what angle that represents. It doesn't matter. If you're really curious, the point 01 is right there. This is kind of what Derek asked me about in the homework. That's a 90-degree angle. Who cares? We don't care about the angle at all. Just the coordinate, and we have it. So, what would be the sine of the mystery angle that this coordinate represents, which we know is 90, but who cares? The sine is the...
0.
Sine's 1.
Sine is 1. 1. What about the cosine?
0.
Is the x. The tangent of this mystery angle? 1 over 0. What's 1? What happens when you divide by 0? Can't do it. So 1 divided by 0, anything divided by 0, we put undefined. How about the cosecant? What do you have to do to this number? So flip 1 over 1. Same thing. Secant. Right, think of that as a fraction. If you flip it, it's 1 over 0. So if you flip 0, you get undefined. If you flip undefined, you're going to get 0. That would be 6 separate problems on a test. I'd give you a coordinate, and I would ask you to do one of these 6. Okay, but if I had you do all of them, I'd count that as 6 questions. Okay, let's do this one. All rules with square roots still apply. Don't leave square roots in the bottom of a fraction, nothing like that. Okay. Hey, what's my sine here? Yep. And my cosine? 1/2. Now, tangent is what over what?
1 over.
It's y over x. Square root 3 over 2 divided by 1/2. Now, when we divide these two fractions, the denominators are the same. So what happens? They cancel. Some people say, well, you take the bottom one, you flip it, and you multiply by the top, same thing. The 2's are going to cancel. And what are you left with? Square root of 3 over 1. You could just put square root of 3. I left it as over 1 because you're going to see when I do something in a second. But yes, square root of 3. Cosecant. What do I have to do to the sine? So that's a good start. 2 over the square root of 3. And now what's wrong with that? You can't leave that in the bottom. So how do you fix it? Multiply by the square root of 3. 2 root 3 over 3. How about the secant?
2.
Yeah, that one's easy because there's no root, so nothing we need to fix. And the cotangent?
1 over 3 over 3.
Yep, so start with that. That's a 3. 1 over the square root of 3. And when you fix it, square root of 3 over 3. Again, that would be 6 separate questions. Yep.
I think I know the answer to this already, but like square root of 3 over 3 does not simplify to square root of 1 over 1, does it?
No.
Okay.
No, because that would just be 1, and this is the decimal 0.57. We don't work with decimals much, though, in this. Okay, I don't want to do all 6. Let's just do 3. I'm not going to worry about those, because if you can get the 3 on the left, I bet you could flip them and get the 3 on the right. What's different about this problem? They gave us an angle. That's great, but I don't need an angle to do unit circle trig. I need the what? I need the point. Think about what we said about unit circle. What's the radius? 1. Where's 90? It's at the top. So what's the coordinate?
0, 1.
You go 1. Now from here, it's the same problem. I think we did that one right here. It's exactly the same question. You had to find the coordinate first. Okay. How about 270? 270 is the bottom. On a circle of radius 1, if you go straight down, you're at 0, -1. And now you could go through and fill the x's and the y's. How about pi? What I might do first is change it to degrees. That's 180. Where's 180 on the circle?
That's a good circle.
-1.
Right, it's left 1. Now you got your coordinate, you can do everything they're asking for. Let's look at this one. What's pi divided, don't look at the 7 for now. What's pi divided by 2? That's 90. What's 90 times 7? 630. Now, that's kind of a big angle. We have a way to make that smaller.
Minus 360.
Minus 360. 270. 270, we just did that. That answer is exactly the same as this one. They're the same problem. There's no difference. Okay? So you might get the same question worded different ways when you convert from radians to degrees. You'll see they're the same. Okay, so that's the homework for tonight.
What's the date today?
Today's date is the 20th.
20th.
Page 324, that's 6.1. 56 to 61, 70 to 73. And then 335, I'll explain what I want. I want you to do 1, 5, and 8. Follow the directions they give you in the book. But I also want you to find the 6 trig functions of 1, 5, and 8. So find the sine, cosine, tangent, secant, cosecant, cotangent. And I'm giving you 3 other ones I want you to find the 6 trig functions for. Okay. Find the 6 trig functions of 3 pi over 2, which we might have just done that. 2 pi, and do it for the coordinate square root 2 over 2, comma square root 2 over 2. Okay, so we'll look at that probably on Friday. I'll check it when you come in right at 7:35. Probably by 7:45 we'll get rolling on the last half of this section. I'll check it at 7:35 tomorrow. When you come in.